Our universe is a vast and mysterious place, filled with wonders that boggle the mind and stretch the imagination. It is filled with billions of galaxies, each containing billions of stars, planets, and other celestial bodies, all bound together by the force of gravity. But how did this incredible expanse come to be? How did the universe, with all its complexity and beauty, originate? The answer, according to modern cosmology, is the Big Bang, a monumental event that set everything into motion. Imagine, if you will, all of space and time compressed into an infinitesimally small point, a singularity, where the laws of physics as we know them cease to apply. This singularity was incredibly hot and dense, containing all the energy and matter that would eventually form everything we see around us today. Then, about 13.8 billion years ago, something remarkable happened. This singularity began to change in a way that would forever alter the course of cosmic history. This singularity began to expand, rapidly and dramatically, in an event that we now call the Big Bang. This expansion wasn't just an explosion of matter into pre-existing space. It was the expansion of space itself, creating the very fabric of the cosmos. This event, this rapid expansion from an incredibly hot, dense state, is what we call the Big Bang, the birth of our universe. In the first fraction of a second, the universe expanded at an unimaginable rate, a period known as inflation, which set the stage for everything that would follow. During inflation, the universe grew from something smaller than an atom to the size of a grapefruit in a fraction of a second, an almost inconceivable transformation. This rapid expansion had a profound effect on the universe, shaping its structure and properties in ways that scientists are still working to fully understand. It smoothed out any initial irregularities, much like inflating a balloon smooths out its wrinkles, leading to a more uniform and homogeneous universe. This smoothing effect explains why our universe appears remarkably uniform on the larger scales, with galaxies and clusters distributed evenly across the cosmos. The Big Bang wasn't just an event in the past, it's an ongoing process that continues to shape the universe. The universe continues to expand and cool to this day, with galaxies drifting apart and the cosmic landscape evolving over billions of years. Understanding the Big Bang is crucial to understanding the universe's origin, evolution, and ultimate fate. It provides a framework for exploring the cosmos and our place within it, offering insights into the fundamental nature of reality itself. In the immediate aftermath of the Big Bang, the universe was an inferno of energy. This cataclysmic event marked the birth of everything we know, setting the stage for the formation of all matter and energy. Temperatures were so high that matter as we know it couldn't exist. The universe was a seething cauldron of unimaginable heat, where even the most basic particles couldn't form stable structures. Instead, energy surged through the nascent universe, a chaotic soup of fundamental particles. These particles, such as quarks and leptons, were in constant frenetic motion, colliding and interacting in a high-energy dance. As the universe expanded, it cooled. This cooling was crucial, as it allowed the energy to gradually transform into matter, setting the stage for the formation of the first particles. This cooling allowed energy to convert into matter and antimatter, particles with opposite charges. These particles began to form in pairs, each particle having a corresponding antiparticle. When matter and antimatter collide, they annihilate each other, releasing a burst of energy. This process was happening constantly, with particles and antiparticles forming and annihilating in a cosmic dance. Luckily for us, there was a slight asymmetry in the early universe, a tiny excess of matter over antimatter. This imbalance, though minuscule, was enough to ensure that some matter survived the annihilation process. This slight imbalance allowed matter to survive and eventually form everything we see in the universe today. Without this tiny excess, the universe would be a very different place, devoid of the stars, planets, and galaxies we observe. As the universe continued to cool, fundamental particles like quarks and gluons combined to form protons and neutrons, the building blocks of atomic nuclei. These particles began to coalesce, forming the first simple nuclei. This process, known as nucleosynthesis, began just minutes after the Big Bang. During this brief but intense period, the universe was a hotbed of nuclear reactions, creating the first light elements. During this period of intense activity, the universe resembled a giant nuclear reactor, forging the light elements that would later seed the first stars. The conditions were perfect for nuclear fusion, allowing these elements to form. The intense heat and pressure of the early universe allowed protons and neutrons to overcome their natural repulsion and fuse together, forming the nuclei of helium, lithium, and a small amount of beryllium. These elements were the building blocks for future cosmic structures. This process, however, couldn't create heavier elements. The conditions in the early universe were not suitable for the formation of elements heavier than lithium. The universe cooled too quickly for larger nuclei to form. As the temperature dropped, the nuclear reactions that could create heavier elements ceased, leaving the universe with only the lightest elements. The heavier elements we observe today were forged much later in the fiery hearts of stars. These stellar furnaces, through the process of stellar nucleosynthesis, created the diverse array of elements that make up the universe as we know it. The early universe was a hot, opaque fog of protons, electrons, and photons, the particles of light. In this primordial soup, the universe was a chaotic and dense environment where particles were constantly interacting with each other. Photons constantly collided with free electrons, unable to travel freely. This incessant interaction created a state where light could not move in straight lines, making the universe opaque and impenetrable to any form of light. This constant scattering prevented light from traveling through the universe as it does today. The universe was essentially a glowing fog, with light bouncing around in all directions, unable to escape the dense environment. Around 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This cooling process was gradual but significant, leading to a monumental change in the universe's structure. This event, known as Recombination, marked a pivotal moment in cosmic history. It was a turning point that set the stage for the universe to evolve into the complex and diverse cosmos we see today. With fewer free for the first time, illuminating the universe in a way that had never been possible before. As the universe that were once constantly scattered were suddenly free to travel unimpeded. This transition was a dramatic shift, transforming the universe from a foggy, impenetrable state to a clear and open expanse. These photons, stretched over billions of years by the expansion of space, make up the cosmic microwave background radiation, or CMB. The CMB is a faint glow that fills the universe, providing a window into the past. This faint afterglow, discovered in 1964, provides us with a snapshot of the universe as it existed just 380,000 years after the Big Bang. It is a relic of the early universe, a time capsule that has preserved the conditions of that era. By studying the subtle temperature fluctuations in the CMB, cosmologists can learn about the universe's early conditions, its composition, and the seeds of the large-scale structures we observe today. These fluctuations are like fingerprints, each one telling a story about the universe's infancy. It holds clues to the fundamental processes that shaped the cosmos, offering insights into the forces and events that have driven its evolution. It's a testament to the incredible journey our universe has taken, from a hot, dense soup of particles to the structured cosmos we observe today. This journey is a story of transformation, from chaos to order, from simplicity to complexity, and from darkness to light. After the brilliant flash of recombination, the universe entered a period known as the Cosmic Dark Ages. With no stars yet formed, the universe was a vast, dark expanse of mostly neutral hydrogen and helium gas. The only light came from the gradually fading glow of the cosmic microwave background. During this era, gravity began to exert its influence on the slightly denser regions of the universe. These denser regions, harboring the seeds of future galaxies, slowly attracted more and more matter from their surroundings. Billions of years. This period of darkness was crucial for the universe's evolution. The subtle density fluctuations that arose from quantum fluctuations in the very early universe had time to grow under the influence of gravity. Of the first stars and galaxies, the Cosmic Dark Ages weren't a time of inactivity. They were a crucial period of gestation, a time when the universe was preparing for the next stage in its evolution, the formation of the first stars and the dawn of a new era. Hundreds of millions of years after the Big Bang, the universe began to emerge from its cosmic slumber. Gravity had been diligently at work, pulling together the dense pockets of gas that had formed during the early universe. As these pockets collapsed under their own gravity, they heated up, eventually reaching temperatures and densities high enough to ignite nuclear fusion in their cores. These were the first stars, much more massive and luminous than our own sun. They blazed with an intense ultraviolet radiation that flooded the surrounding universe. These first stars were cosmic pioneers, ushering in a new era of light and warmth. The intense radiation from these stellar giants had a profound effect on the surrounding neutral hydrogen gas. The ultraviolet photons stripped electrons from the hydrogen atoms, a process known as ionization. This marked the beginning of the epoch of reionization, a period when the universe transitioned from being mostly neutral back to a state of ionization. The first stars lived short but brilliant lives, eventually exploding as powerful supernovae. These explosions scattered the first heavy elements, forged in their stellar cores, into the surrounding space. These elements would later become the building blocks of planets, moons, and even life itself.